Kia ora, Year 12. This is a really nice old exam question from the 2008 integration paper, and it's very like one that we put in the Wellington College school exam last year, although I got to say this one is a little bit easier. So if you want to go and do this one and then afterwards watch the 2017 question, or I haven't actually done that one yet, but worked solutions are up on EWC. If you're watching from another school, I might try and video it later. So in this case, we've got a shaded region. So we're finding the area between two curves. So the first thing to think about is the usual way that we do this is we integrate and we do the top function, which we call f of x, and the bottom one, which we call g of x. And we integrate that with respect to x. So in this case, we've got one of them is sine of kx, and the other one is sine squared of kx. The first thing that I'm going to do is think about where they meet. Now, one of these curves is a sine curve, and so its maximum value is going to be 1. And that means that everything we're working with in here is a decimal between 0 and 1, right? So all values in this bit of the sine kx curve are between 0 and 1, and that means that when I square that number, I'm going to have sine squared of kx being less than sine of kx. So that's useful because it tells me straight away that sine of kx will be f of x, the top curve, and the sine squared will be the bottom curve. If you were going on further or doing things with cosine and sine, you've got to be really careful with switch-arounds there. But in our case, the only thing we've got to do here is we've got to figure out what is that value there where they intersect. So to do that, I'm going to solve where are the two y values equal, and that's going to give me my limits of integration. So 1 will obviously be 0. Right, but solving sine kx is equal to sine squared kx, I get this. So remember, we never divide through by the sine kx, or I'm going to get rid of a solution. So we've got sine squared kx minus sine kx. Factorising, I get sine of kx into sine of kx minus 1. So sine of kx equals 0, or sine of kx equals 1. So let's think about our sine curve. Where will sine of kx be 0? In that first bit, well, kx is 0, so that's how we get our x equals 0 solution, and we saw that one already on the picture above. Sine of kx equals 1, that will happen. I'm just working in this first bit of the curve, so kx will equal pi on 2, 90 degrees. So my top limit of integration is going to be x is equal to pi over 2k. So now we're ready to go because we've worked out which one's the top curve and which one is the bottom curve. So we've got pi on 2k here, 0 down here. Sine of kx minus sine squared of kx. And we're integrating all of that with respect to x. Now when I look at the sine squared, I should straight away think that the double angle cosine formula is going to help me. I'm going to do a little bit of work in a bubble to figure out how I can integrate sine squared of kx, and I always go right back to the basic formula. I've got 3 choices. The one that I want is the one with sine squared in it. So cos of 2 theta is 1 minus 2 sine squared theta. Rearranging that gives me 2 sine squared theta is 1 minus cos 2 theta. Remember, the reason we want to do this is that cos of 2 something is really easy to integrate. Sine squared is not possible as it stands. Then I get sine squared of, and I'll substitute my kx now, sine squared of kx is going to be 1/2 minus 1/2 cos of 2kx. So I've done that bit of working in a little box. Now I'm going to substitute this back into here. So we'll call this a. We can rewrite it now as a is equal to this integral. So sine of kx is going to be easy to work with. And now we've got this. Okay, so it's time to do the integration. if you're being really slow and careful in the exam, you could rewrite another line with the minus a half and then the plus, but I'm going to skip that step so that you don't all switch off your YouTube out of boredom. Okay, so anti-differentiating, I want to end up with sine. It's going to be cos of kx. When I differentiate that, I'll get negative sine. I want positive sine, so it's going to be negative 1 over k because of the chain rule application. So that's the first term. This will give me minus x on 2. Now I've got plus a half cos 2x. So I'm going to have 1 over, we'll have something with a sine 2kx, and I need to divide out the 2k. Okay, I'm happy with the sign of the sine, because when I differentiate sine, I get positive cosine, and that's what I want here. So let's just see if I've missed anything there. No, that looks all right. Okay, so now our limits of integration are not that nice. So we've got pi on 2k and 0 here. Just want to have a little bit more look here and see if I've made a mistake. Nope, I think that's okay. I'm sure someone will leave me a comment if I have made a mistake or done something else wrong. I'm going to substitute in now, and it turns out that this ugly limit here is quite nice once we start popping everything in. So the first set of terms gives me negative 1 over k cos of k times pi over 2k minus pi over 4k plus 1 over 4k sine of 2k pi on 2k. That's the first bit done. Now a lot of these are going to be 0 in the next batch, but not all of them. So we've got negative 1 over k cos of 0 minus 0 plus 1 over 4k sine of 0. So you can see lots of stuff simplifying already. Just have to be really careful you don't muck this last bit up, because this is the easy part. So negative 1 over k and cos of pi on 2 is 0 minus pi on 4k plus 1 on 4k sine of pi, so that's going to be 0, plus 1 on k, because this is 1, minus 0 plus 0. So we're left with a whole lot of zeros. We've got 1 over k from here, sine of pi is 0, 1 over k minus pi over 4k. Now, I'm sure that would get a big tick, but I'm going to make that look more beautiful. Common denominator will be 4k, and I'm going to have 4 minus pi on 4k. All right, so that's the end of what I think is a really nice excellence question. I'd love to see something like that in this year's paper. Not sure if we will or not. It's got quite a lot of trig in there, so if you haven't done the trig internal, you're probably at a big disadvantage. So maybe that's a reason why they wouldn't ask it anymore. But there you go. Leave me any questions or comments if you've got them.